What if I told you that the most water-efficient farming method wasn't invented by Silicon Valley, but by Persian engineers 2,500 years ago? And what if modern farms could achieve dramatic water reduction by combining these ancient underground channels with today's IoT sensors and AI scheduling? The answer lies in precision irrigation systems that treat every drop of water like a measured ingredient in a recipe. Instead of flooding entire fields, smart sensors detect exactly when and where plants need water, then deliver it through automated drip systems with surgical precision. But how did Persian engineers move water through hundreds of miles of desert without a single pump or electric motor? Persian engineers accomplished this feat through an underground network called qanats. These systems tapped into aquifers buried deep beneath mountain ranges, channeling water through precisely graded tunnels that could span vast distances. The qanat represented more than simple excavation. It required mathematical precision to maintain consistent water flow across terrain that rose and fell unpredictably. The engineering challenge centered on gradient control. Each tunnel required a slope steep enough to maintain water flow, but gentle enough to prevent erosion and structural collapse. Too steep, and rushing water would undermine the tunnel walls. Too shallow, and sediment would accumulate, blocking the channel entirely. Persian engineers achieved this balance by calculating grade ratios that modern hydraulic engineers still reference today. Master craftsmen called muqannis spent their entire careers perfecting qanat construction. These specialists descended into vertical shafts every 20 to 30 meters, excavating horizontal channels in complete darkness. The muqannis worked by candlelight, breathing stale air while carving through rock and hard-pan soil. Cave-ins claimed countless lives as these engineers pushed deeper into mountainside, following water tables that shifted seasonally. The construction process began with locating underground water sources through surface indicators like vegetation patterns and seasonal springs. Once muqannis identified a viable aquifer, they dug the mother well, the deepest shaft that would tap directly into the water table. From this central point, they excavated a gently sloping tunnel toward the intended irrigation area, sometimes located dozens of kilometers away. Vertical access shafts punctuated the tunnel route at regular intervals. These shafts served multiple functions, removing excavated soil, providing ventilation for workers, and enabling ongoing maintenance access. The spacing between shafts followed standardized patterns that balanced construction efficiency with structural integrity. Workers hauled soil to the surface using leather buckets and primitive windlass systems, creating the distinctive crater-like mounds that still mark ancient qanat routes across Iran and neighboring regions. Scale distinguished qanats from other ancient irrigation methods. Individual systems stretched over 40 kilometers, connecting mountain aquifers to agricultural valleys separated by vast distances. Construction of major qanats required multiple generations to complete. Fathers trained sons in muqanni techniques, passing down knowledge of soil composition, structural engineering, and water flow dynamics through apprenticeship systems that lasted decades. These elaborate networks represented coordinated efforts involving hundreds of workers across multiple communities. Each qanat required ongoing maintenance teams who descended into the tunnels annually to clear sediment, repair structural damage, and extend channels as water tables fluctuated. The qanat network around Kashan stands as a testament to this engineering mastery, recognized by the FAO as part of the globally important agricultural heritage systems, acknowledging its significance in sustainable land use and its capacity to address contemporary challenges through ancient knowledge. Underground flow provided crucial advantages that surface irrigation could never match. Subterranean channels eliminated evaporation losses entirely, preserving every drop from source to destination. Desert heat that claimed massive percentages of surface water through evaporation had no impact on qanat delivery systems. The underground environment maintained consistent temperatures year-round, preventing the thermal shock that could damage crops irrigated with surface water during extreme weather. Natural filtration occurred continuously as water moved through carefully constructed gravel beds and sand layers integrated into tunnel floors. This filtration removed sediments and organic matter that would otherwise clog distribution systems or harm crops. The filtered water emerged cleaner and more suitable for irrigation than most surface sources, reducing the need for additional treatment or settling ponds. Persian engineers designed distribution systems that divided water flow with mathematical precision. Carefully calibrated gates and channels allocated specific volumes to different agricultural zones based on crop requirements and land ownership agreements. These distribution networks incorporated measurement devices that tracked water usage, enabling equitable sharing among multiple farming communities served by individual qanat systems. The efficiency achieved by mature qanat systems exceeded those of many modern irrigation methods. While traditional flood irrigation typically loses 30 to 40% of applied water through evaporation, runoff, and deep percolation, qanats delivered the vast majority of extracted water directly to crop root zones. This efficiency resulted from eliminating surface exposure and controlling flow rates through precisely engineered channels. Maintenance protocols ensured consistent performance across centuries of operation. Qanat management teams developed specialized tools for underground excavation, structural repair, and sediment removal. These teams maintained detailed knowledge of seasonal water table fluctuations, enabling proactive adjustments to extraction rates and tunnel depths. Regular maintenance schedules prevented small problems from becoming system failure. Geographic distribution of qanat technology extended far beyond Persia, reaching into Central Asia, North Africa, and parts of Europe through trade and conquest routes. Each region adapted the basic qanat principles to local geological conditions and water sources. These adaptations proved the flexibility of underground irrigation concepts across diverse environments and agricultural systems. The qanat legacy influences modern precision irrigation through its fundamental principle of controlled water delivery. Persian engineers demonstrated that efficiency depends on eliminating waste rather than increasing extraction capacity. Their underground channels delivered water exactly where needed, when needed, without excess application or environmental losses. This principle of precision targeting required water masters who could read soil conditions through decades of accumulated experience, assessing moisture levels and crop needs through careful observation and intuitive understanding of agricultural rhythms. Modern technology replaces that intuitive expertise with IoT soil sensors that function as digital water masters, detecting moisture variations that would escape even the most skilled traditional farmers. These electronic devices measure changes as subtle as individual droplets penetrating soil layers, monitoring conditions continuously across entire field systems where ancient qanat engineers once relied on visual cues and tactile assessment. Traditional irrigation scheduling operates on predetermined timetables that ignore actual soil moisture levels and current weather conditions. Farmers typically water crops based on calendar schedules, seasonal averages, or visual observations that often miss critical moisture deficits until plant stress becomes visible. This approach leads to chronic overwatering in some areas, while other zones suffer from insufficient moisture, creating inefficient water distribution that wastes resources while potentially harming crop yields. Capacitance-based soil sensors measure electrical conductivity changes that occur as soil moisture content fluctuates throughout the day and across seasonal cycles. These probes detect the electrical properties of soil-water solutions, which vary predictably based on moisture levels. As water content increases, electrical conductivity rises correspondingly, providing precise measurements of soil saturation at specific depths and locations. The sensors convert these electrical readings into moisture percentages, delivering quantitative data that replaces subjective moisture assessment methods. Data transmission occurs through wireless protocols that send measurements in real time to centralized monitoring systems. This frequent monitoring captures rapid moisture changes caused by irrigation events, rainfall, or accelerated plant uptake during peak growing periods. The continuous data stream enables immediate irrigation adjustments that respond to actual field conditions rather than predetermined watering schedules. Sensor networks communicate through low-power communication protocols designed specifically for agricultural environments, where devices must operate reliably across vast distances while consuming minimal battery power. Network architecture connects individual sensor nodes through mesh communication systems that relay data across fields without requiring direct cellular or internet connectivity at every measurement point. Gateway devices collect data from multiple sensors within their communication range, then transmit consolidated information to cloud-based monitoring platforms through cellular, satellite, or fixed broadband connections. This distributed approach ensures reliable data collection even in remote agricultural areas with limited telecommunications infrastructure. Multi-level probe technology tracks moisture conditions simultaneously across different soil depths, providing comprehensive understanding of water distribution throughout the crop root zone. Surface sensors monitor moisture in the top soil layer, where initial water application occurs and evaporation effects are most pronounced. Root zone probes measure moisture availability at depth, where active plant roots extract water for growth and metabolic processes. Deeper sensors track subsoil moisture levels that indicate water percolation rates and potential drainage issues that could lead to waterlogging or nutrient leaching. Advanced sensor networks incorporate multiple measurement points across individual fields, creating detailed moisture maps that reveal spatial variations in water needs. Different soil types, elevation changes, and microclimatic conditions within single fields often create zones with distinct water requirements that uniform irrigation cannot address effectively. Sensor arrays identify these variations, enabling zone-specific irrigation that delivers appropriate water volumes to different field areas based on actual measured conditions rather than field average estimates. Temperature sensors integrated with moisture probes provide additional data that influences irrigation timing and water application rates. Soil temperature affects root activity, nutrient availability, and evaporation rates, all of which influence optimal irrigation scheduling. Combined temperature and moisture data enable more sophisticated irrigation decisions that account for seasonal variations, daily temperature cycles, and weather-related changes that affect plant water uptake patterns. Battery life optimization ensures continuous operation throughout growing seasons without frequent maintenance interventions. Modern agricultural sensors incorporate power management systems that balance measurement frequency with energy consumption, extending operational periods to match seasonal agricultural cycles. Solar charging capabilities enable indefinite operation in field environments with adequate sunlight exposure, eliminating battery replacement requirements during critical growing periods. Data validation protocols prevent irrigation decisions based on faulty sensor readings that could result from equipment malfunctions, soil disturbances, or environmental interference. Multiple sensors within local areas provide redundancy that identifies outlier readings requiring investigation or sensor recalibration. Data quality checks compare current readings with historical patterns and neighboring sensor data to flag potentially erroneous measurements before they influence irrigation systems. Integration with weather monitoring enhances soil sensor data by incorporating rainfall predictions, humidity levels, and evapotranspiration rates that affect soil moisture dynamics. Weather data helps interpret sensor readings within broader environmental contexts, distinguishing between moisture changes caused by irrigation, natural precipitation, or atmospheric conditions. This integration prevents unnecessary irrigation before predicted rainfall events and adjusts watering schedules based on upcoming weather conditions that will affect soil moisture levels. Real-time alerts notify farm managers when soil moisture levels drop below predetermined thresholds specific to different crops and growth stages. These notifications enable proactive irrigation responses that prevent plant stress before it impacts growth rates or yield potential. Threshold settings account for crop-specific water requirements, seasonal growth patterns, and soil characteristics that influence optimal moisture ranges for different agricultural systems. Performance data demonstrates the effectiveness of precision irrigation systems, with documented water usage reductions of up to 40% across various crop types, while simultaneously achieving 10% increases in crop yields. These improvements result from eliminating guesswork in irrigation timing and water application volumes. The continuous feedback loop transforms raw sensor measurements into actionable irrigation decisions, but processing this massive stream of environmental data requires computational power that can analyze multiple variables simultaneously and generate precise watering recommendations faster than any human operator could manage. Machine learning algorithms hosted on cloud platforms like AWS process this environmental data through artificial intelligence irrigation models that function as decision engines, simultaneously evaluating dozens of variables to determine optimal watering schedules for individual plants across vast agricultural operations. These systems integrate real-time soil moisture readings, satellite weather data, crop growth stage indicators, and evapotranspiration calculations to generate irrigation recommendations that adapt continuously to changing field conditions. Unlike human operators who might consider 3 or 4 factors when making watering decisions, AI models evaluate comprehensive data streams that include atmospheric pressure, wind velocity, solar radiation intensity, and soil temperature variations measured at multiple depths throughout crop root zones. The complexity challenge emerges from balancing immediate soil conditions against predicted weather patterns, while accounting for optimal plant growth windows that vary by crop type and seasonal development stages. Current soil moisture readings might indicate irrigation needs, but incoming rainfall predicted within 12 hours could make watering unnecessary or potentially harmful through oversaturation. Plant stress indicators from multispectral imaging might suggest water deficiency, but growth stage analysis could reveal that reduced irrigation actually promotes root development during specific phenological phases. AI systems must weigh these competing factors while maintaining irrigation schedules that support optimal yield outcomes. Algorithm inputs include real-time weather satellite data that provides precipitation forecasts, temperature projections, humidity measurements, and wind pattern analysis updated throughout growing seasons. Historical precipitation patterns spanning decades enable AI models to recognize seasonal weather trends and drought probability calculations that influence long-term irrigation planning. Crop coefficient tables specify water requirements for different plant varieties at various growth stages, from germination through harvest maturity. Soil texture analysis determines water infiltration rates, drainage characteristics, and moisture retention capacity that affect irrigation timing and application volumes across different field zones. Weather satellite integration provides atmospheric data covering temperature gradients, cloud formation pattern, barometric pressure changes, and precipitation probability calculations extending several days into future forecasting periods. Research demonstrates that precision irrigation systems effectively combine satellite imagery, weather forecasts, and hydraulic models to optimize water delivery decisions. Evapotranspiration modeling combines temperature, humidity, wind speed, and solar radiation measurements to calculate water loss rates from soil surfaces and plant transpiration processes. These calculations determine baseline water replacement requirements that irrigation systems must meet to maintain optimal soil moisture levels for sustained plant growth and development. Machine learning adaptation enables AI systems to refine irrigation recommendations based on outcomes from previous watering cycles, adjusting algorithms to account for local environmental conditions and crop response patterns specific to individual farming operations. These systems analyze correlations between irrigation timing, water application volumes, and resulting crop performance metrics, including growth rates, yield measurements, and quality indicators. Continuous learning processes identify optimal irrigation parameters that maximize water use efficiency while maintaining or improving agricultural productivity across seasonal variations and annual climate fluctuations. Predictive modeling capabilities extend AI irrigation recommendations several days ahead of current conditions through weather pattern recognition algorithms that analyze atmospheric data trends and seasonal climate patterns. Advanced forecasting models incorporate climate oscillation indices, jet stream positioning, and regional weather system movements that influence local precipitation probability and temperature variations. These predictive capabilities enable proactive irrigation scheduling that anticipates plant water needs before stress conditions develop, preventing yield reductions caused by insufficient moisture during critical growth periods. Neural network architectures process vast data sets encompassing soil conditions, weather variables, crop characteristics, and historical irrigation outcomes to identify complex relationships between environmental factors and optimal watering schedules. Deep learning algorithms recognize patterns within multidimensional data streams that reveal subtle connections between variables that traditional analysis methods might overlook. These sophisticated processing capabilities enable AI systems to optimize irrigation decisions based on comprehensive understanding of agricultural ecosystems rather than simple threshold-based watering triggers. Real-time processing occurs continuously as AI algorithms evaluate incoming data streams and generate updated irrigation recommendations as new environmental measurements or weather forecast updates become available. Edge computing capabilities enable local data processing at farm locations, reducing response times and ensuring irrigation decisions can proceed even during temporary communication disruptions with centralized cloud-based systems. Distributed processing architectures balance computational loads across multiple processing nodes, maintaining system responsiveness during peak data processing periods. AWS-based AI irrigation systems demonstrate measurable benefits beyond beyond water conservation, achieving reduced fertilizer runoff that helps prevent soil and water contamination while generating lower operational expenses by minimizing energy, labor, and equipment requirements. Automated decision-making protocols translate AI recommendations into specific irrigation commands that control valve operations, pump scheduling, and water distribution across different field zones without requiring human intervention. These systems respond to environmental changes rapidly, enabling immediate irrigation adjustments that maintain optimal soil moisture conditions throughout daily temperature cycles and sudden weather changes. Integration with farm management systems enables AI irrigation models to coordinate water scheduling with other agricultural operations, including fertilizer application, pest management activities, and harvest planning that might influence irrigation timing or water requirements. AI systems generate irrigation schedules that adapt continuously to evolving field conditions. But these digital decisions require precise translation into physical water delivery mechanisms that can respond rapidly to AI-generated commands while maintaining surgical accuracy in water placement. Drip irrigation systems deliver water through networks of plastic tubing punctuated by precisely engineered emitters that release controlled volumes directly into soil surrounding individual plant root zones. These distribution networks eliminate the broadcast application methods used by sprinkler systems, which spray water across entire field surfaces regardless of where plants actually grow. Instead of saturating large areas with uniform water application, drip systems target specific locations with measured volumes calculated to meet exact plant requirements without excess application that leads to runoff, deep percolation, or evaporation losses. Traditional irrigation leads to significant water wastage, reaching up to 10 gallons per minute per acre compared to 3 to 7 gallons per minute per acre for alternative techniques like drip irrigation. Flood irrigation achieves water use efficiency rates between 60 and 70%, losing substantial volumes through surface evaporation, uncontrolled runoff, and deep percolation beyond root zones where plants cannot access applied water. Sprinkler irrigation improves upon flood methods, but still loses significant water through wind drift, evaporation during application, and overspray onto non-productive areas between crop rows. Pressurized irrigation systems like drip networks demonstrate substantially higher water use efficiency than gravity systems through precise placement and controlled application rates. The efficiency differential results from fundamental differences in water delivery mechanisms. Flood irrigation saturates entire field surfaces, creating conditions where excess water moves beyond crop root zones through gravitational drainage or remains on soil surfaces where evaporation claims large percentages of applied volumes. Drip systems apply water slowly and directly to soil areas where plant roots can immediately access moisture, minimizing losses through all major inefficiency pathways that affect traditional irrigation methods. Pressure compensating emitters represent the crucial hardware component that enables consistent water delivery across varied terrain and system pressure conditions. These devices incorporate internal flow regulation mechanisms that maintain steady discharge rates regardless of elevation changes, tubing length variations, or pressure fluctuations within distribution network. Standard emitters would deliver higher flow rates at lower elevations and reduced volumes at higher points within irrigation systems, creating uneven water application that defeats precision irrigation objectives. Internal diaphragm mechanisms within pressure compensating emitters automatically adjust flow passage dimensions as system pressure changes, maintaining consistent discharge rates across operating pressure ranges typically encountered in agricultural irrigation systems. These self-regulating devices ensure uniform water application, whether emitters operate at the beginning of irrigation zones near high-pressure main lines or at distant locations where pressure drops due to friction losses through extended tubing runs. Automated valve systems control water flow to different irrigation zones based on crop-specific requirements, soil conditions, and real-time environmental data collected through sensor network. Individual zones receive irrigation schedules tailored to particular crop varieties, growth stages, soil characteristics, and microclimate conditions that influence water needs across different field areas. Zone-specific control eliminates the compromise irrigation schedules required by systems that cannot differentiate between areas with varying water requirements. Solenoid-operated valves respond to electronic control signals generated by irrigation management systems that process data from soil moisture sensors, weather monitoring equipment, and crop management databases. These automated controls enable simultaneous management of multiple irrigation zones across extensive agricultural operations, with each zone receiving precisely timed water applications calculated to maintain optimal soil moisture levels for specific crops and growth conditions. Multi-stage filtration systems prevent clogging within drip irrigation network while maintaining consistent water quality throughout distribution systems that extend across hundreds or thousands of acres. Primary filtration removes large particles, organic debris, and suspended sediments that could obstruct emitter passages or accumulate within tubing network. Secondary filtration screens capture smaller particles that pass through initial filtration stages but could gradually accumulate within emitters or create flow restrictions in narrow tubing sections. Screen filters, disc filters, and media filters operate in sequence to progressively remove contaminants of different sizes and characteristics from irrigation water supplies. Backwash systems automatically clean filtration components during predetermined maintenance cycles or when pressure differential indicators signal filter loading conditions that reduce system performance. Automated backwash procedures reverse water flow through filter elements, flushing accumulated debris through waste outlets without interrupting irrigation operations in other system zones. Integration protocols connect drip irrigation hardware with digital control systems that process sensor data, weather information, and AI-generated irrigation recommendations into specific valve operation commands and zone-specific watering schedules. Communication interfaces translate digital irrigation decisions into physical system responses within minutes of receiving updated environmental data or revised irrigation requirements. The growing adoption of pressurized irrigation demonstrates this technology's proven effectiveness. In the western United States, pressurized irrigation increased from 37% of all irrigated cropland acres in 1984 to 74% in 2023, reflecting widespread recognition of efficiency advantages over traditional methods. These integrated precision irrigation components create the foundation for documented efficiency improvements, but the true measure of success emerges when farms combine all these technologies into unified management systems that deliver measurable results across real agricultural operations. Case studies from over 9,000 sensors deployed across 1,200 farms worldwide documented the breakthrough that transformed precision irrigation from experimental technology into proven agricultural methodology. These comprehensive implementations achieved 40% water reduction targets, while simultaneously improving crop yields by 10% across diverse farming environments. The combination of real-time environmental monitoring, predictive analytics, and precision water delivery created documented outcomes that validated integrated precision irrigation systems across multiple agricultural environments and crop types. Commercial farming operations faced significant integration challenges when connecting sensor networks, weather monitoring systems, AI processing platforms, and automated irrigation hardware into cohesive decision-making ecosystems. Individual technologies performed effectively within isolated applications, but achieving optimal efficiency required seamless data flow between disparate systems manufactured by different companies using incompatible communication protocols. Integration complexity increased exponentially as farm operations scaled across multiple field zones with varying soil types, crop varieties, and microclimatic conditions. Platform integration solutions emerged through comprehensive agricultural management systems that standardize data collection, processing, and control protocols across multiple technology components. These unified platforms translate sensor measurements, weather forecasts, and crop management data into standardized formats that AI algorithms can process uniformly, regardless of original equipment manufacturers or communication protocols. Centralized management enables coordinated irrigation decisions that account for interactions between different field zones and optimize water allocation across entire farming operations. Successful implementations incorporated soil moisture sensors positioned at multiple depths throughout crop root zones, weather monitoring stations providing real-time atmospheric data, and automated valve systems responding to AI-generated irrigation commands within predetermined timeframes. These integrated systems eliminated traditional irrigation scheduling based on fixed timetables or visual crop assessment, replacing subjective decision-making with quantitative analysis of comprehensive environmental data sets. Efficiency mechanisms targeted the primary sources of water waste in traditional irrigation systems through systematic elimination of overwatering, evaporation losses, and mistimed applications that failed to coincide with optimal plant uptake periods. Overwatering occurred when irrigation systems applied water volumes exceeding plant requirements or soil retention capacity, leading to runoff and deep percolation beyond root zones where crops could not access applied water. Precision irrigation prevented overwatering through continuous soil moisture monitoring that triggered irrigation only when soil conditions dropped below crop-specific thresholds. Evaporation losses affected traditional irrigation methods through surface water exposure during application and post-application periods, when excess moisture remained on soil surfaces or plant foliage. Drip irrigation eliminated most evaporation losses by delivering water directly into soil matrices surrounding plant root zones, minimizing surface exposure that enabled atmospheric moisture extraction. Automated timing systems further reduced evaporation by scheduling irrigation during optimal environmental conditions when temperature, humidity, and wind patterns minimized atmospheric water loss potential. Irrigation timing optimization aligned water applications with periods of maximum plant uptake capacity, typically during early morning hours when atmospheric conditions favored root absorption while minimizing evapotranspiration losses. AI algorithms processed environmental data to identify optimal irrigation windows that balanced soil moisture requirements against atmospheric conditions, crop development stages, and predicted weather patterns that could influence water uptake efficiency. Consistent soil moisture levels achieved through precision irrigation maintained optimal growing conditions that reduced plant stress and enabled efficient nutrient absorption throughout crop development cycles. Traditional irrigation methods created moisture fluctuations that stressed crops during dry periods and potentially damaged root systems during oversaturation events. Precision systems maintained soil moisture within narrow ranges, optimized for specific crop varieties and growth stages, creating stable growing environments that supported consistent plant development. Plant stress reduction occurred through elimination of moisture deficit periods that triggered defensive responses, including reduced photosynthesis, stunted growth, and premature fruit development that decreased yield quantity and quality. Consistent moisture availability enabled plants to maintain optimal metabolic processes throughout growing seasons, supporting maximum yield potential while improving crop quality characteristics valued in commercial markets. Economic analysis revealed substantial operational cost reductions through decreased water consumption, reduced energy requirements for pumping and distribution, and improved crop yields that increased revenue per acre while reducing input costs per unit of production. Water cost savings accumulated across irrigation seasons as precision systems eliminated waste application while maintaining or improving crop performance. Energy savings resulted from reduced pumping requirements when irrigation volumes decreased without compromising agricultural productivity. These systems also achieved reduced fertilizer runoff that helps prevent soil and water contamination while generating lower operational expenses through minimized labor, equipment maintenance, and resource allocation requirements. Labor cost reductions occurred through automation systems that eliminated manual irrigation scheduling, valve operation, and field monitoring tasks that traditionally required significant human resource allocation throughout growing seasons. Automated systems operated continuously without labor supervision while providing detailed operational data that improved long-term agricultural planning and resource allocation decisions. The documented efficiency gains demonstrated the practical feasibility of achieving substantial water conservation while maintaining agricultural productivity necessary for food security and farm economic viability. These ground-based monitoring systems provided comprehensive field-level data, but detecting crop stress before it becomes visible to human observation requires monitoring capabilities that extend far beyond what sensors positioned at soil level can detect. Satellite imagery offers a daily overview of agricultural landscapes, detecting plant stress indicators through multispectral imaging sensors that capture light wavelengths invisible invisible to human vision, revealing crop health problems days before ground-based observation could identify declining plant conditions. These orbital monitoring systems function as aerial intelligence networks that continuously survey farming operations, collecting data that guides precision irrigation decisions across vast agricultural areas worldwide. Advanced remote sensing technology transforms satellite platforms into comprehensive crop monitoring systems that supplement ground-based sensor networks with broad-scale environmental analysis. Human visual detection of plant stress relies on observable symptoms, including leaf wilting, color changes, and reduced plant vigor that become apparent only after stress conditions have progressed to levels that may already impact crop yields and quality. Farmers traditionally identify irrigation needs through walking field perimeters, observing plant appearance, and assessing soil conditions through tactile examination methods that provide limited spatial coverage and delayed stress detection. Visual assessment methods miss early-stage stress indicators that occur at cellular levels before manifesting as visible plant symptoms. Multispectral imaging systems capture electromagnetic radiation across multiple wavelength bands, including visible light, near-infrared, and thermal infrared spectrums that reveal plant physiological processes invisible to standard photography or human observation. Near-infrared wavelengths reflect differently from healthy versus stressed vegetation because chlorophyll absorption patterns change as plants experience water deficits, nutrient limitations, or disease pressure. Thermal imaging detects temperature variations across crop canopies that indicate transpiration rate changes associated with water stress conditions before visible symptoms appear. Vegetation indices, calculated from multispectral satellite data, provide quantitative measurements of crop health, biomass density, and stress levels across individual field zones with mathematical precision that eliminates subjective interpretation inherent in visual crop assessment methods. Normalized difference vegetation index calculations compare near-infrared and red light reflectance ratios to determine chlorophyll content and photosynthetic activity levels that indicate overall plant health status. Enhanced vegetation index measurements account for atmospheric interference and soil background effects that can distort vegetation assessments in standard index calculations. Crop water stress indices utilize thermal infrared measurements combined with visible wavelength data to calculate canopy temperature differentials that indicate plant transpiration rates and water availability status within crop root zones. Elevated canopy temperatures relative to surrounding air temperature suggest reduced transpiration caused by water stress conditions that restrict plant cooling mechanisms. Temperature differential calculations provide early warning indicators of developing water stress before soil moisture sensors detect significant moisture depletion at root zone depths. Custom algorithms convert raw satellite imagery into actionable agricultural intelligence through automated analysis systems that identify stress patterns, calculate vegetation indices, and generate field-specific irrigation recommendations based on detected crop conditions. Machine learning processing systems analyze historical satellite imagery combined with ground truth data to refine stress detection accuracy and reduce false positive indicators that could trigger unnecessary irrigation applications. Automated image analysis eliminates manual interpretation requirements while providing consistent stress assessment criteria across multiple agricultural seasons and diverse crop types. Stress zone mapping creates detailed field-level analyses that identify specific areas requiring irrigation attention while distinguishing between zones with adequate moisture levels that do not require water application. Spatial analysis algorithms generate irrigation prescription maps that specify water application rates and timing recommendations for different field zones based on satellite-detected stress levels and predicted crop water requirements. These detailed maps enable precision irrigation systems to target water applications to areas with demonstrated need while avoiding unnecessary irrigation in adequately hydrated zones. Resolution capabilities of modern agricultural satellites provide sub-meter spatial accuracy that enables identification of stress conditions affecting individual crop rows or small field sections rather than field average conditions that might mask localized problems requiring targeted intervention. High-resolution imaging distinguishes between crop stress caused by irrigation inadequacy versus other factors including pest damage, disease pressure, or nutrient deficiencies that require different management responses. NASA's GRACE satellites demonstrate the broader applications of satellite technology in agricultural water management, being used to assess overall changes in groundwater levels in California's Tulare Basin, providing crucial data for regional water resource planning. This capability extends satellite monitoring beyond individual farm management to watershed-scale water availability assessment that influences agricultural planning across entire regions. Publicly accessible platforms like FAO Waypor and NASA Surveyor provide near real-time satellite data that supports water availability assessments, making advanced monitoring technology available to farming operations worldwide, regardless of their individual technology investment capacity. These platforms democratize access to satellite-based agricultural intelligence that was previously available only to large commercial operations with substantial technology budgets. Integration protocols combine satellite-derived stress indicators with ground-based sensor networks, weather monitoring systems, and soil moisture measurements to create comprehensive irrigation management datasets that account for multiple environmental factors influencing crop water requirements. Data fusion algorithms synchronize satellite observation schedules with ground sensor measurement intervals to provide coordinated monitoring that captures both broad-scale field conditions and localized environmental variations. Real-time processing systems analyze satellite imagery within hours of data collection, enabling irrigation responses that address detected stress conditions before they progress to levels affecting crop productivity or quality outcomes. Automated alert systems notify farm managers when satellite analysis identifies developing stress conditions requiring irrigation attention within specific time frame to prevent yield impacts. Comprehensive monitoring through integrated satellite and ground-based systems provides the environmental intelligence necessary for strategic agricultural decisions that extend beyond irrigation timing to fundamental questions about which crops can thrive under specific water availability constraints. AI-driven crop recommendation systems analyze regional water availability, soil conditions, and climate patterns to identify agricultural alternatives that dramatically reduce irrigation requirements while maintaining economic viability for farming operations. These sophisticated algorithms process decades of agricultural data, weather records, and market analysis to recommend crop varieties that align plant water needs with local environmental conditions. Strategic crop selection represents a fundamental shift from forcing water-intensive crops to survive in arid environments toward cultivating plants naturally adapted to water-limited conditions. Economic pressures complicate crop selection decisions as farmers must balance water conservation objectives against established market demands, existing infrastructure investments, and proven agricultural practices that generate reliable income streams. Traditional crops like corn and cotton command well-established markets with predictable pricing structures, processing facilities, and distribution networks that farmers depend on for economic stability. Transitioning to drought-tolerant alternatives requires developing new market relationships, learning unfamiliar cultivation techniques, and potentially investing in different harvesting or processing equipment that increases financial risk during adoption periods. Water requirement analysis reveals dramatic differences in irrigation needs across various crop categories, with some traditional staples demanding exceptional water volumes, while drought-adapted alternatives achieve comparable yields using significantly reduced amounts. These differences become particularly critical in regions experiencing severe groundwater depletion, such as the Indian states of Punjab and Haryana, where widespread use of flood irrigation in rice farming has driven aquifer levels to unsustainable depth. Strategic crop transitions in these areas focus on replacing water-intensive rice cultivation with drought-tolerant alternatives that maintain agricultural productivity while reducing groundwater extraction. Drought-tolerant legumes demonstrate remarkable water efficiency compared to conventional grain crops, with chickpeas requiring substantially less water per kilogram of harvested protein while providing nitrogen fixation benefits that reduce fertilizer requirements for subsequent crops. Lentils achieve similar water efficiency ratios while offering high protein content and diverse culinary applications that support both human consumption and livestock feed markets. These legume alternatives provide comparable nutritional value to traditional grains while reducing overall field water demand by 60 to 70%. Ancient grains, including sorghum, millet, and quinoa, evolved in arid environments where survival depended on efficient water utilization and tolerance for irregular precipitation patterns. Sorghum production requires significantly less water than corn cultivation, while providing similar carbohydrate content and livestock feed applications. Pearl millet thrives in semi-arid conditions with minimal water requirements, offering drought resilience that enables cultivation in regions where conventional grains fail consistently. Soil salinity adaptation capabilities enable specific crops to maintain productivity in degraded agricultural land, where salt accumulation from previous irrigation practices has rendered soil unsuitable for conventional crop production. Quinoa demonstrates exceptional tolerance for saline soils, producing viable harvests in conditions containing salt concentrations that would kill most traditional grain crops within weeks of germination. Barley varieties adapted for saline conditions can tolerate moderate soil salt levels while maintaining grain quality suitable for brewing, livestock feed, and human consumption applications. Climate matching algorithms incorporate regional precipitation pattern, temperature ranges, humidity levels, and seasonal weather variations to identify crop varieties with optimal adaptation potential for specific geographical locations. These systems analyze historical climate data spanning multiple decades to predict crop performance under various weather scenarios, including drought years, excessive rainfall periods, and temperature extremes that could affect agricultural productivity. Machine learning algorithms continuously refine recommendations based on actual crop performance data collected from farms implementing alternative crop strategies. Regional water availability assessments guide crop selection by quantifying renewable water resources, groundwater depletion rates, and competing water demands from urban, industrial, and environmental uses that limit agricultural water allocation. Areas experiencing declining groundwater levels or increased competition for surface water resources require crop selections that minimize irrigation dependency while maintaining agricultural productivity sufficient for farm economic viability. In drought-prone regions of California, such as almond orchards in Central Valley, thermal emission and vegetation indices guide transitions to more water-efficient crops like pistachios, which require substantially less irrigation while maintaining comparable economic returns. Productivity optimization through strategic crop selection focuses on maximizing agricultural output per unit of water consumed rather than maximizing yield per acre, regardless of water input requirements. Water productivity calculations compare crop yield values against total water consumption, including irrigation, precipitation, and soil moisture utilization, to identify varieties delivering optimal economic returns relative to water resource investments. These analyses often reveal that drought-tolerant crops generate higher profitability per liter of water consumed compared to high-yielding varieties requiring intensive irrigation. Market positioning strategies for drought-tolerant crops emphasize premium pricing opportunities available through organic certification, sustainable agriculture branding, and specialty food markets that value environmentally responsible production methods. Ancient grains command premium prices in health-conscious consumer markets seeking nutritional diversity and sustainable agricultural practices. These premium markets enable farmers to maintain or improve income despite potentially reduced yields per acre compared to conventional crops. Field-level water demand reductions of 60 to 80% become achievable through systematic crop selection that prioritizes water-efficient varieties adapted to local environmental conditions. These reductions occur through eliminating irrigation requirements during drought-resistant crop establishment periods and reducing ongoing water applications throughout growing seasons. Strategic crop selection transforms agricultural water management from intensive resource consumption toward efficient resource utilization that aligns agricultural production with renewable water availability. Even the most water-efficient crops require some irrigation during critical growth periods, creating opportunities to multiply available water resources through advanced collection and storage technologies that capture precipitation when it occurs and release it strategically when crops need it most. Automated collection systems transform seasonal rainfall into year-round irrigation capacity through underground rainwater storage technology that functions as a water multiplication system. These Advanced harvesting systems capture precipitation during brief seasonal periods and store collected water in underground reservoirs, engineered for gradual release throughout extended dry seasons. Strategic placement and engineering design enable individual catchment areas to generate irrigation water sufficient for crop production across areas significantly larger than original collection zones. Traditional passive rain collection relies on simple gravity-fed systems that capture precipitation in surface tanks or ponds, where substantial volumes are lost through evaporation and seepage during storage periods. These conventional approaches provide minimal water multiplication benefits because storage losses consume significant portions of collected rainfall before irrigation applications occur. Passive systems lack the sophisticated distribution controls necessary for strategic water release, aligned with crop development schedules and soil moisture requirements. AI-optimized harvesting systems integrate weather prediction algorithms with automated capture and distribution mechanisms that maximize water collection efficiency while minimizing storage losses through precisely timed release schedules. Predictive weather modeling enables harvesting systems to prepare storage capacity before major precipitation events, while optimizing collection strategies based on storm intensity forecasts and seasonal rainfall patterns. Automated controls coordinate water capture, storage management, and distribution activities to ensure maximum water retention and strategic allocation throughout agricultural seasons. Smart monitoring networks track precipitation patterns, soil moisture levels, and crop water requirements to generate harvesting schedules that align water collection with upcoming irrigation needs. Machine learning algorithms analyze historical weather data combined with real-time atmospheric measurements to predict optimal harvesting windows and storage management strategies. These intelligent systems eliminate manual decision-making while optimizing water resource utilization across seasonal cycles and annual climate variations. Pungru underground storage technology captures monsoon rainfall through engineered infiltration systems that channel surface water into deep underground storage chambers constructed within natural geological formations or artificially created cavities. This innovative system filters, injects, and stores excess stormwater in large underground reservoirs that eliminate evaporation losses entirely while providing natural filtration through soil layers that improve water quality during storage periods. Underground storage maintains consistent temperatures that preserve water quality and prevent algae growth common in surface storage facilities. The Pungru system utilizes vertical injection wells that rapidly transport surface runoff into underground storage zones during heavy precipitation events when soil surface infiltration rates cannot accommodate intense rainfall volumes. High-capacity injection systems prevent surface flooding while maximizing water capture efficiency during brief monsoon periods that provide majority annual precipitation in many agricultural regions. In January 2024, Pungru was awarded Top Innovator in the Zero Water Waste Challenge, launched by the Aquapreneur Innovation Initiative, a project of the World Economic Forum's Uplink with HCL Group, recognizing its breakthrough approach to water resource multiplication. Distribution mechanisms within Pungru systems incorporate controlled release valves that gradually extract stored water based on crop irrigation schedules and soil moisture monitoring data. Pressure-regulated release systems maintain consistent flow rates regardless of storage level variations, while providing precise volume control aligned with precision irrigation requirements. Underground distribution networks transport harvested water directly to crop production areas through buried pipeline systems that eliminate additional evaporation losses during water transport. Drone-mapped watershed analysis identifies optimal collection point placement through comprehensive topographical surveys that calculate surface water flow patterns during precipitation events. Geospatial modeling algorithms process elevation data, soil infiltration rates, and seasonal runoff patterns to determine catchment zone boundaries and predict water collection volumes under various rainfall scenarios. Precision mapping enables strategic placement of collection infrastructure to maximize water capture efficiency while minimizing construction costs and environmental disruption. Automated distribution systems integrate harvested rainwater with conventional irrigation networks through sensor-controlled mixing valves that blend stored water with groundwater or surface water supplies based on water quality requirements and availability constraints. Smart blending systems optimize water resource utilization by prioritizing harvested rainwater during peak irrigation periods while preserving stored volumes for drought emergency applications. Integrated distribution networks provide seamless water delivery regardless of source combinations while maintaining consistent water quality and application timing. Quality monitoring instruments track stored water conditions, including dissolved oxygen levels, pH balance, and bacterial contamination indicators that could affect crop health or irrigation system performance. Automated treatment systems inject oxygen, adjust pH levels, or apply sanitization treatments when monitoring systems detect water quality degradation during extended storage periods. Continuous quality management ensures harvested water remains suitable for irrigation applications throughout storage cycles lasting several months. Water multiplication effects demonstrate the remarkable efficiency of advanced rainwater harvesting systems. All the rainwater falling on a piece of land can be harvested in a bungru, which would be sufficient to supply water to irrigate at least 4 times the area of the land used for harvesting. These systems reduce groundwater extraction demand while creating drought resilience through stored water reserve that remain available during extended dry periods. This fourfold multiplication enables sustainable agricultural expansion in water-limited regions where conventional irrigation approaches would exceed renewable resource availability. Standardized data platforms enable coordinated implementation of rainwater harvesting technologies across regional agricultural networks where shared infrastructure and management protocols maximize water conservation benefits at landscape scales. These platforms create the foundation for connecting individual farm innovations into comprehensive agricultural intelligence network that can scale precision irrigation benefits across diverse farming communities worldwide. Agricultural data ecosystems function as the foundational infrastructure that enables smallholder farmers in developing regions to access the same precision irrigation intelligence that guides commercial agricultural operations across technologically advanced farming systems. These comprehensive platforms standardize data collection, processing, and distribution protocols that transform localized sensor measurements and environmental monitoring into globally accessible agricultural intelligence networks. Universal data access eliminates the technological barriers that previously restricted advanced irrigation management to well-funded agricultural enterprises with substantial technology investment capacity. The connectivity challenge emerges from bridging vast digital divides between high-technology farming regions equipped with comprehensive sensor networks, high-speed internet connectivity, and sophisticated data processing capabilities versus resource-limited agricultural areas where farmers operate with minimal technological infrastructure and intermittent communication access. Traditional precision agriculture platforms require constant internet connectivity, expensive sensor hardware, and specialized technical expertise that remains unavailable in many agricultural regions where water conservation could provide the greatest environmental and economic benefits. Government-supported agricultural data platforms represent coordinated efforts to democratize precision agriculture technology through publicly funded infrastructure development that provides universal access to environmental monitoring, weather forecasting, and irrigation optimization services. These national platforms aggregate data from multiple sources, including government weather stations, satellite monitoring systems, and research institutions to create comprehensive agricultural intelligence networks accessible through basic mobile communication devices rather than requiring sophisticated computing infrastructure at individual farm locations. Kenya's agricultural data sharing platform allows both private entities and government to have access to shared agricultural data categories encompassing crops, livestock, weather, soil, pest, and diseases. The platform processes data from government weather monitoring stations, research institution sensor networks, and satellite observation systems to generate location-specific irrigation recommendations accessible through standard mobile phone interfaces. Farmers receive automated text messages with irrigation timing recommendations, rainfall predictions, and soil moisture assessments tailored to their specific geographic location conditions and crop selections. India's Agricultural Data Exchange System represents a collaborative initiative by the government of Telangana, the Indian Institute of Science, and the World Economic Forum's Center for the Fourth Industrial Revolution, India. The platform coordinates information sharing between government agencies, research institutions, and private technology providers to create comprehensive agricultural intelligence networks that serve both large commercial operations and individual smallholder farmers through standardized data interfaces. The system aggregates weather data, soil condition monitoring, market pricing information, and technical assistance resources into centralized databases accessible through multiple communication channels, including mobile applications, voice-based systems, and community information centers located in rural agricultural regions. Ethiopia's National Soil and Agronomy Data Sharing Policy demonstrates another approach to democratizing agricultural intelligence through coordinated government initiatives that standardize environmental monitoring and crop management information across diverse agricultural regions. These policy frameworks establish data collection protocols and sharing mechanisms that enable comprehensive agricultural intelligence networks while protecting farmer privacy and maintaining data security standards. Interoperability standards establish common data formats, communication protocols, and interface specifications that enable seamless information exchange between sensor networks manufactured by different companies, weather monitoring services operated by various organizations, and irrigation control systems deployed across diverse agricultural operations. Standardized data formats eliminate compatibility barriers that previously prevented integration between different technology components, enabling farmers to combine sensors, weather services, and control systems from multiple suppliers into cohesive precision irrigation management systems. Edge computing solutions provide local data processing capabilities that maintain precision irrigation functionality even when internet connectivity proves unreliable or temporarily unavailable in remote agricultural regions. Distributed processing systems deploy computing resources at farm locations where data analysis occurs locally using standardized algorithms downloaded during periodic connectivity windows. Local processing capabilities ensure continuous irrigation optimization even during communication disruptions, while synchronizing with centralized platforms when connectivity becomes available. Mobile network optimization enables precision agriculture platforms to function effectively through standard cellular communication infrastructure available in most agricultural regions worldwide. Data compression algorithms reduce communication bandwidth requirements while maintaining irrigation decision accuracy, enabling effective platform operation through basic mobile communication services rather than requiring high-speed broadband connectivity unavailable in many rural agricultural areas. Democratization of precision agriculture technology occurs through standardized platforms that eliminate economic barriers, preventing smallholder farmers from accessing advanced irrigation optimization capabilities previously exclusive to well-funded commercial agricultural operations. Universal access models enable farmers with minimal technology investment to receive the same environmental monitoring, weather forecasting, and irrigation scheduling services that guide decision-making at large-scale agricultural enterprises. Training and support programs ensure effective technology adoption through comprehensive education initiatives that teach precision irrigation principles, platform operation procedures, and irrigation system maintenance techniques tailored to local agricultural practices and technological literacy levels. Extension service integration provides ongoing technical assistance that enables successful long-term adoption of precision irrigation technologies across diverse agricultural environments and farmer experience levels. These standardized data platforms create the technological foundation for precision irrigation scaling. But translating digital capabilities into widespread agricultural adoption requires innovative financing mechanisms that make advanced water conservation technology economically accessible to farming communities regardless of their initial investment capacity. Cooperative financing models enable agricultural communities to overcome the substantial upfront investment barriers that traditionally restrict precision irrigation technology to large commercial farming operations with significant capital resources. These innovative funding approaches distribute technology costs across multiple farmers who jointly invest in shared sensor networks, automated irrigation systems, and data processing infrastructure that individual farms could not afford independently. Shared ownership structures transform precision irrigation from exclusive industrial technology into accessible agricultural tools that enable water conservation across diverse farm operations, regardless of individual economic capacity. High upfront costs for comprehensive precision irrigation systems often exceed annual farm income for smallholder agricultural operations, creating insurmountable economic barriers that prevent technology adoption despite proven efficiency benefits and long-term cost savings. Individual sensor networks capable of monitoring soil moisture across meaningful agricultural areas require thousands of dollars in hardware investments before accounting for installation, maintenance, and data processing expenses. Automated irrigation control systems add substantial additional costs for valve networks, distribution infrastructure, and integration services that compound initial investment requirements beyond individual farmer financial capacity. Shared infrastructure models distribute these capital expenses across farmer cooperatives, where multiple agricultural operations contribute proportional investments based on irrigated acreage, crop types, and expected water savings benefits. Cooperative members jointly purchase sensor equipment, automated control systems, and data processing services while sharing operational costs, including maintenance, technical support, and system upgrades throughout technology life cycles. Cost distribution enables individual farmers to access comprehensive precision irrigation capabilities for investment levels equivalent to traditional irrigation system maintenance expenses rather than requiring complete system replacement funding. Farmer group investments typically organize around geographic clusters where adjacent agricultural operations can share sensor networks and irrigation control infrastructure while maintaining independent crop management and irrigation scheduling decisions. Regional cooperatives coordinate bulk purchasing agreements that reduce per-unit costs for sensors, automation equipment, and technical services through volume discounts unavailable to individual farm purchasers. Shared technical expertise within cooperative structures enables knowledge transfer and troubleshooting support that reduces ongoing operational costs while improving system performance across member farms. Blended climate finance mechanisms combine public sector environmental funding with private agricultural investment to subsidize precision irrigation adoption through carbon credit programs, environmental conservation incentives, and water resource protection initiative. Financial institutions and donors co-invest to reduce upfront risk and encourage private sector participation in agricultural technology deployment. These public-private partnerships recognize water conservation benefits that extend beyond individual farm operations to include regional water resource preservation, carbon sequestration through improved soil management, and reduced agricultural environmental impact that benefit broader community interests. Private sector agricultural technology financing demonstrates proven effectiveness through programs like PepsiCo's Precision Conservation Management Program, which funds irrigation tech for farmers in Nebraska. These corporate partnerships provide direct technology investment while securing sustainable supply chain relationships with agricultural producers implementing water conservation practices. Private sector funding enables rapid technology deployment across agricultural regions while achieving corporate sustainability objectives and supply chain risk reduction goals. Carbon credit mechanisms generate revenue streams for farmers implementing precision irrigation systems that reduce energy consumption through decreased pumping requirements and improve soil carbon sequestration through optimized water management practices. Precision irrigation contributes to climate change mitigation by reducing agricultural energy consumption, minimizing fertilizer runoff that produces greenhouse gas emissions, and improving soil health that enhances carbon storage capacity. International carbon markets provide ongoing payments for measurable emission reductions achieved through precision agriculture adoption, creating long-term financial benefits that offset initial technology investment costs. Index-based insurance products protect farmers against drought-related crop losses while providing premium discounts for agricultural operations, implementing precision irrigation systems that demonstrate reduced drought vulnerability through improved water use efficiency. These specialized insurance policies utilize weather data and satellite monitoring to trigger automatic claim payments during drought conditions that affect regional agricultural production, eliminating traditional crop damage assessment procedures that delay compensation payments. Insurance premium reductions for precision irrigation adopters recognize documented risk reduction benefits while providing financial incentives that encourage water conservation technology implementation. Parametric insurance triggers activate compensation payments based on predetermined weather conditions, including rainfall deficits, temperature extremes, and soil moisture levels measured through objective monitoring systems rather than subjective crop damage assessments. Automated claim processing reduces administrative costs while providing rapid compensation that enables farmers to maintain operations during drought periods without accumulating debt or abandoning precision irrigation investments during temporary financial stress. Microfinance institutions develop specialized lending products tailored to precision irrigation investment requirements, providing structured payment schedules that align with seasonal agricultural income cycles and water savings benefits realized through improved irrigation efficiency. Agricultural lending programs incorporate precision irrigation technology benefits into loan qualification criteria, recognizing improved farm productivity and risk reduction that justify favorable interest rates and extended repayment terms. Risk assessment algorithms used by agricultural lenders increasingly recognize precision irrigation adoption as positive indicators that reduce default probability through improved farm productivity, reduced drought vulnerability, and enhanced operational efficiency that stabilizes agricultural income streams. Technology adoption serves as risk mitigation demonstration that qualifies farmers for mainstream agricultural financing programs. These comprehensive financing approaches create sustainable pathways for precision irrigation expansion across diverse agricultural regions and economic conditions without requiring massive public sector investment or exclusive reliance on farmer capital resources. Successful cooperative financing models enable water conservation technology to extend beyond elite agricultural operations toward universal adoption across global food production systems, where efficiency improvements provide the greatest environmental and humanitarian benefits. The transformation from cooperative financing to widespread implementation demonstrates how technological innovation becomes accessible through strategic economic partnership. The path to 40% water reduction combines the precision principles of ancient Persian engineers with the real-time intelligence of modern digital systems. Persian muqannis achieved near-zero water loss through underground qanat networks that delivered water exactly where needed. Today's IoT sensors, AI algorithms, and automated drip irrigation systems replicate this surgical precision using digital intelligence instead of mathematical calculations carved into stone. The most revolutionary solutions emerge from honoring traditional wisdom while embracing technological innovation. If you want to explore how other ancient techniques are transforming modern agriculture, let me know in the comments and I'll make it happen. What surprised you the most about integrating 25-century-old engineering with cutting-edge artificial intelligence?